Hi, I'm Zahra Asiri, a PhD student in mathematics. Today, I will share data-driven framework for evaluating brain stimulation in a rodent migraine model and how it helps us understand pain recovery. Chronic pain disrupts brain activity in complex ways, and many treatments fall short. Electrical stimulation is promising, but we do not yet know which settings are most effective. This study tests different stimulation frequencies and voltage to see how they influence brain recovery after pain. Here is how the experiment was designed. First, we record baseline brain activity from four regions related to pain. Pain then was induced using a 3% formalin injection into the bar. After that, the rat received 12 different electrical stimulation sessions, each followed by 3 minutes rest phase. During this rest period, brain signals were recorded again. These stress phases are what I analyzed to evaluate recovery. The experiment was led by Diana April under the guidance of Dr. Yang Peng. My work began after data collection, where I developed a statistical framework for analyzing recovery under the mentorship of Dr. Maya Bedro. This diagram shows the full experiment timeline and the 12 stimulation setting used. The experiment started with a 5 minutes baseline shown in blue. Then comes pain induction and 20 minutes of mentoring. After that, the 12 stimulation session began. Each labeled S1 to S12. Each sessions use a different frequency and voltage combination. For example, S1 used 1 Hz at 5 voltage, S12 used 100 at 100 voltage. 100 Hz at 100 voltage. After each session, there are 3 minutes rest phase R1 to R12 where brain activity is recorded. These recordings are the focus of my analysis. Our goal is to is our goal is our goal is simple. Which stimulation setting helps the brain recover best after pain? To answer this, I compare each rest phase to the pain-free baseline using a custom method that handles the complexity of the brain data. Here's how it works. One, sampling. I randomly sample time points from the full baseline to build a reference matrix. Second, segmentation. I divided each rest phase into short equal-length time windows. Distance computation. For each window, I compute intra-matrix similarity, how stable it is internally, intermatrix similarity, how closely it matches the baseline. Intra-matrix similarity tells us how internally consistent the brain signals are during each rest phase. Higher similarity to the baseline means better recovery. Top performance here are rest 11, rest 2, rest 12, and rest 4. Intermatrix similarity tells us how well each rest phase blends with the baseline when their signals are mixed. The closer the patterns are, the better the recovery. Rest 6, rest 9, rest 1, rest 10 ranked highest in this category. Overall, recovery ranking to combine both tested, I used Fisher method, which merged the intra and intermatrix result. Rest 12 came out on top. It showed the highest similarity to the baseline and was linked to the most intense stimulation 1 Hz and 100 voltage. Rest 6 and rest 9 also performed well. At the bottom, rest 1 showed the least recovery. In short, high frequency, high voltage stimulation, especially 1 Hz and 100 voltage, was the most effective at helping the brain return to normal state. Rest 1 consistently ranked highest across all measures. Stronger, faster stimulation may support better recovery from pain. This approach introduced a simple, scalable way to evaluate brain recovery using pairwise distance. In the future, I plan to apply more advanced methods like permutation test, kernel approach, or mainformed learning to uncover even deeper insights. Thank you.